Let's review the last couple of formulas we did. We talked about a standard deviation. And don't forget. What is a standard deviation? What is a deviation? Deviation simply means to go off course. And since we're dealing with, we first talked about measures of central tendencies, the mean, median, mode. The variance and deviation will now talk to us about how far, because if it's a mean, the mean is pretty much the middle, the average. So that means there's numbers to both sides in order for this to be the average, the mean. What we're interested in now is how do these numbers on both sides, how do they behave? How far are they on the, how much is this left group and how far is this right group away from the mean? That's what deviation is all about. Deviation tells us what is the average distance from all the numbers on both sides of the mean. And we had two formulas. The first one is pretty straightforward. It's the one that you usually refer to when you first do deviations. What does X bar stand for? Ooh, okay, here's, what do all of these mean?
X bar means mean.
X bar means mean. What is X tilde, the squiggle?
The median.
Very good. And the X dot? Mode. Yeah, because remember, mathematics is a language, and each of these symbols tells us what we're looking for. That's like on the standard deviation. What it looks for is the X by itself is simply our data points. So what this formula tells us is we take each data point minus the mean. Now what that means is if the numbers to the left of the mean, we'll get a negative number. If the X is bigger than the mean, we'll get a positive number. Now, to get rid of all the negatives, that's why we square it. And then we add them all up. And then to get rid of the squares, we square root. So that's what gives us the standard deviation in the simplest form. Then we saw another formula. Again, it deals with the square root of the entire equation. N times summation of x squared minus the summation of x squared over n times n minus 1. Notice on top, it means two different things. You notice that the square is on the inside of the parentheses, so you square the x's first, and then you add them. This one, you add up all the x's, and then you square it. That's what order of operations tells us. So let's go ahead and let's look at another example we did yesterday, and then we'll move on from there. Example 3. Find the standard deviation of this data set. 50, 25, 75, 35, 50, 25, 30, 50, 45, 25, and 20. And we should have 11 pieces of data. Our objective is to find S. S is the standard deviation. So the first thing we do, okay, since we have a relatively small data set here, we can go ahead and list each one of them separately. But if we had any more, really, any more than 12 or 15, then we use intervals or a frequency table. So even here, if we went to, we could put this in order. We have 20, 25. There's another 25. There's a 30. 35. 45. 3 50s. And a 75. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I'm missing one. There's another 25. So there should be 3 25s. That's right. Always, always, always check to make sure you always have the right number of data points. So what's my next column going to be? Oh, what do I have to do next? Remember, look at the formula. The formula says summation of x minus x bar squared over n minus 1. We have x. What else do we need? We need to find x bar. How do we find the x bar? What's the formula for x bar? Summation of all your data divided by how many you have. So add up all your x's. Three. 300. It's 45 for S 90. That's 50 and 50. That's 100. 200. 300. 80. That one. That one. 50 and 50. 50, 50. And we have 90 left. 1, 2, 3, 4. 430 divided by 11 So actually, you all should be checking these out also. So don't just sit there and wait me to do it. What'd y'all get? 39.9? 0.1? Why 0.1? Yeah, very good. Why is it 0.1? Why is it one decimal place? No. What's the rule about rounding?
If it's higher than
One.
5, then you round it up.
Yes, but why is it only one decimal place? Why not two decimal places? Remember the rule there? The rule is you always have one decimal place more than your original data. Since this data had no decimal places, our answers are going to be one decimal place. If we had one decimal place here, our final answer would be two decimal places. So it's always one more decimal place than your original data has. Okay, so there's your mean, 39.1. What do we do with this number? Look at the formula. What do we have to do first? We have X in order of operations. You have to do inside the parenthesis first. We have X, that's this. We have to subtract X bar. So we have to find X minus X bar. So we have to take each one of these minus 391. So it's all the X's minus 39.1. If you haven't done it, then do it again. Don't just sit there. Do the work. So these are all the what should this column equal? It should equal 0. And if it doesn't, so if you did something wrong, go back and check them again. So we got negative 19.1, negative 14.1. Negative 4.1, 5.9. All right, so it should equal 0 if we add them up. So what's our next step? Yep. Because we have negatives here, that makes it 0. We have to get rid of the negatives. So we take each one of those and square them. And that's what our formula says up here. Before we add them, we got to do the x minus x bar squared. And then we'll add up all those answers. So go ahead and square each of these. You need some paper? You sure? So I have a whole bunch.
It's okay. I can do it.
Okay. So what we have to do here. Square.
What is square? Do I use this one? Right
The,
here?
the one that has an x with a power 2 on it.
So this one.
Yes, I believe so. Yes.
This one.
It's one that looks like this with it has a 2 up here. Because yeah, all the numbers you enter, those are the x's. Just so just to see if you're on the right track. So if we add them up, we get 0. So what we do is get rid of the negatives. That's why we square them. So we should come up with this. So what's the next step? According,
Plug it in into the equation.
right, because now that we added them all up, we got 2740.9. That's the summation of the x minus x bar squared. That goes on top. 2740.9.
14.1 times 198.89.
Which one are you talking about?
The second one, 14.1
Mm-hmm.
times 14.1 is 198.81.
Well, actually, what's happening here, whenever you use a computer like this number here is really that. So when I square this number, I get that. It's called a round off error. And that's the difference between if you use a computer, a calculator, or if you do it by hand. Because it's not really 14.1. Because what this number really is that number. And if you square this number, you'll get that answer. Oop. So yes, you're absolutely correct. If we just took these numbers as is. Okay, let me see those then. So we have 19.1 squared, 14.1 squared, 14.1 squared. And even if we just did those numbers as is, we'll still get 2740.9. What's our n? And so on the bottom, we have 11 minus 1. So that becomes 2740.9 divided by 10 becomes, move the decimal over 1. So we have 274.09. And if we square root that one, what'd you get? 16.56, or actually it should be 16.6. Because remember, your final answer has to be one decimal away from those. So what is the purpose? Why do we have to find the standard deviation? Because the whole goal of what we're trying to do is called normalize our data. We're trying to see how all of it sits around our mean. We know our mean is what, 39.1. Our standard deviation is 16.6. Whenever we talk about statistics, probabilities, we always look at something called significance. We have a rule of thumb. This is the rule of thumb. What do you think that means? That's what it says, but what does it mean? And it does have a lot more meaning. We'll get to it shortly. But what this means is if we had our data set, this is our mean. If we take X bar plus, this is X bar plus 2 standard deviations. And this is X bar minus 2 standard deviations. For significance, if it's below this number, then that is significantly low. If it's above, what do you think that's called? Right. What do you think everything between there is? Not significant. The reason it's not significant is because it's very close to the mean, so it really doesn't influence it that much. So everything to the right here are significantly high values, and everything to the left is significantly low values. Okay, so let's look at what we have here with this information. What is the mean? 39.1. What is 2S? What would that be? What is S? Yeah, so it's 2 times 16.6, which is 33.2. So what we do here is we start from our mean, 39.1, and then we add and subtract 33.2 from it. So this is minus 2S, this is plus 2S. So what numbers would go there? So this is going to be minus 33.2, and this is going to be plus 33. So what are we adding and subtracting from and to? What number are we dealing with? 39.1. So 39.1 minus 33.2 is? Anybody? Who's got a calculator? How about this other number? So these are the numbers that are plus 2 and minus 2 standard deviations from the mean. That means any number less than 5.9 is significantly low. Anything greater than 72.3 is significantly high. That's pretty cool. That's pretty interesting because now we have a way to judge our numbers. We're also going to find out pretty soon about how many numbers fit in each of these standard deviations. Because if this is 2 standard deviations, then there must be a 1 standard deviation on both sides. Right? So we can add and subtract the standard deviations and keep on going out further. Obviously, we can see that the standard deviation is a valuable number, but what we're looking for, that's deviating from the mean. How about variance? How far it varies from the mean? So we have of the sample and of the population. Now, of all of the formulas we're going to learn in this course, this has got to be the easiest one. Because for a sample, we take the deviation and square it. There you have it. That's the variance of a sample. What symbol do we use for population? The little squiggly O thingy. And it shows rho squared. This is the RHO, the Greek rho. Or the Greek lowercase s. By definition, the variance is a set of values, is a measurement that is the square of the deviation from the mean. It's the square of the deviation. Remember, S is a deviation. We square it, it becomes variance now. So what happens mathematically when we square the deviation? What do we get? What's the formula for deviation? That's the deviation. If we square it, what's that going to give us? What happens on the right-hand side? When you square it, what happens to it? What does what? What happens to the square root?
You find the square root of the summation of.
No, the square root and the square cancel each other out. They're inverses, they're opposites of each other. There's your variance. In algebra, the square root, if you square it, these cancel. If you have a cube root and you cube it, these cancel. So that's when we square it, we get rid of the radical. Okay. Now, what we have to do now is we're going to look at whenever you have, y'all remember this symbol? What does it mean? What's the name of it? What does it do? What's that? Close. It does deal with real numbers, yes. Should play hangman. I'll give you the clues. Absolute value. It measures a distance. It measures the distance of how far a number is from zero. Distances do not have signs. For example, if we were in Arlington, it's in the middle. If here's Arlington, Fort Worth is there. Dallas is there. Let's say they're both 23 miles away. So is Dallas negative 23 miles away and Fort Worth is positive 23 miles away? Or how far is Dallas from Arlington? Do we ever say go it's Arlington? Oh, Dallas is 23 negative 23 miles over there. No, distances do not have signs. It's just how far is it from this point, from your zero to the end point. So because of that, it gets rid of any number. So if we had a -3 inside there, the answer would be 3. Only takes, it erases the negative of the answer inside the absolute value. Because it's a value you're looking for. Let's do some more examples. What's this answer going to be? Yeah,
2.
right, because 3 minus 5 is -2. Order of operations, you have to do inside there first. The reason it's -2 is because 5 is bigger than 3, it's negative. So 5 minus 3 is 2. Now, since we only have one value inside there, it becomes 2. How about this one? Order of operations. The first thing we do are special operations. What's the absolute value of -3? This still stays out in front. So the answer is -3. You cannot distribute in an absolute value. Now, why am I showing you all this? Is because the formula that we commonly use for absolute value is this. So there's X. We take -3 and square it. What is -3 squared? -3 times -3. Negative makes it positive. It's 9. What's the square root of 9? So that is a definition of how we represent the absolute value as an equation. We use that to define this. The mean absolute deviation. Again, mathematicians do not have a creative bone in their body. What does mean mean? Or yeah, it's the middle is the average. Even roughly, even though we're not supposed to say it, it means average. Absolute is those bars, and deviation. All these things. So what that means is the mean absolute, the MAD, we call this MAD, is equal to the summation of all of our X minus X bars over N. Notice it's not the same as we earlier had. For deviation, we don't have n-1 on the bottom. Because the n-1 helps us remove any possible errors we may have. But in this one, since we don't do anything else, just add them up and subtract. This is all we have. So if you're asked to find the mean absolute deviation, you use this formula. So back to this last example. Remember the x minus x bar? We had this. What would you do here? Here, we would take the absolute value of the x minus x bar. So each one of these just becomes positive. So we get rid of all the negatives and so on and so forth. We only get positive numbers. And then divide by n. Okay. Is it a far stretch? Is this one a far stretch from this equation? Not really. Algebraically, we can take this summation and the absolute value, the square root, the radical, and move it to top and bottom separately. Since this is the square root of the whole thing, you can break them up. That's the rule of math. If you have a fraction, a rational expression, you can break them up top and bottom. That's what we did. Remember how we defined absolute value? We defined absolute value as the square root of something squared. The square root of something squared. So this is summation of the absolute value over the square root of n-1. Let's look at this. The square root of x squared is the absolute value of x. The square root, this squared, so it becomes that. So now, since we square root, this is the only big difference. Instead of the square root of the n-1, we simply have n, and that gives us our mat. It's the average because we divide by how many we have. It's absolute because we defined the square root of something squared as the absolute value. And it's a deviation. It's deviation because we have an x minus x bar. I know you guys. You can impress your friends at the next party with this. So any questions about that? So you do the same thing as we just did in the last time. But now all we have to do is take all these numbers, all the positive numbers, add them all up, whatever this number is, divided by n, and that's our MAD. So we would add up all of those and divide by n, and that's our MAD. Here's the empirical 65, 95, or 68, 95, 99.7% rule. Empirical. Empirical simply means it has solid data. It has proof for it, as opposed to speculative, where it's just made up and not really verified. Now, what do these represent? It's funny that these represent standard deviations. Let's start putting everything together. A while back, I showed you this. What is that called? This is called a bell curve. And the middle number, the highest point here, is your average, is the mean, which means that 50% of your data is over here, 50% of your data is over here. True? Because you have to have 100% of your data. We talked about that earlier. Now we just calculated standard deviations. We have 1 standard deviation, 2 standard deviation, 3 standard deviations on both sides. So there's our mean. This is the 1S, 2S. I know my handwriting is horrible. It's not 15, 25, 30. It's 1S, 2S, 3S. Because I get myself mixed up that a lot of times also. This is the S. It's not a 5. It's 1 standard deviation. So now how does this relate to what we just talked about? Within 1 standard deviation, approximately 68% of your data will fall there. 1 standard deviation from both sides of your mean, 68% of your data falls there. Within 2 standard deviations, 95% of your data falls there. Within 3 standard deviations, yeah, 99.7% of your data fall within 3 standard deviations of your mean. And this, give or take some numbers, percentage of error, this, and no matter what data set you have, you will see this, the numbers being very, very, very close, if not exactly that amount. Now, these are approximate. These numbers are approximate. In reality, since both of these are equal and they equal 68%, how much percent on both sides? It's actually 34.15% on both sides. From empirical data. This is just an approximation because you don't want decimal places here. So as you'll see, you'll get that. Okay, now let's look at what percent is in these? Let's do this mathematically. So let's figure out how much goes in here in both of these lines.
47.5?
In each one of those?
Yes.
Okay, well, what you're looking at is you're taking this as 95%, right? So half of this is 45. Well, 45 minus this is what? How much? Is it 12 or 15? So 45 minus 34.15.
So 45, that's half of 9, now 95.
What's that?
That's 95%.
Well, the whole thing is 95. This whole thing is 95%. Since it's half of it, this part here is only 45. Because it's half of 95. Or no, 47.5. Yeah, 45. So minus 34.15. This is 47.5 minus 34.15. And the last one, the third standard deviation, it takes care of 99.7%. Oh, no, we can, since we know that this is 95%, so 99.7 minus 95 is 4.7. So 4.7 has to go in both of these. Divide it by 2, we get 2.35. And then how much is in the very long tails? Well, no, because we know that in the third standard deviation is 99.7. What else is left? 0.3. What's half of 0.3? 0.15. This is how bell curves work when teachers use those to grade. The top 0.15% of the class will make A. The next 2.35 will make a B. The next will make a C. The next is a D, and the 50% will fail. That's why it's not fair to have, it's not, well, I say it's not fair. That's why students don't, you should not like a bell curve. Because you're guaranteed that 50% is going to fail. No matter what you make. If everybody made it in the 90s and you made it in 91, you failed. That's how bell curves work. So if our mean was 20 and our standard deviation was 3, how would our bell curve work? What values would we have? Find me the values for all 3 standard deviations, both direction. This is 20. What's this one? And this one? 20 minus 3 is 17.
14.
And 14.
Yeah.
11, yeah. So remember, these are -3 standard deviations, what those things are. And this is +3. So +3, +3, +3, -3, -3, -3. Let's look at example 6. Example 6 says the empirical rule. IQ scores have a bell-shaped distribution, meaning the mean is 100 and the standard deviation is 15. What percent of IQ scores are between 70 and 130? Since we're dealing with a bell shape, it says bell shape. The mean is 100. Well, and the standard deviation is 15. So one standard deviation makes it 115, 130, 145. And going backwards, we got 85, 60, and then 45. So between 70 and 1, is 70. So between 70 and 130, that's 2 standard deviations. Which means there are approximately 95% of the data that falls between that.
What's 70? Means we're not using 15 as the duration. I think the 70 should be between 85 and 60. I think the 70 should be between 85 and 60. If you're going by the 15.
Well, no, because
duration.
15, if we take 100 minus 15, we get 85. Then we take 85 minus 15, we get 70. So that's why later on, we will look at, let's say we had 62. In order to use numbers that are not on the standard deviations, we'll have to use a table in back. And I'll give you that table. But for right now, we're going to use simple, straightforward. It's always going to be on the deviations. But this only works if it's standard deviation, if it's a bell curve. What if it's not a bell curve? Okay, first off, when we use the bell curve, we call that normally distributed. So if you're, I can say we have a bell curve or the data is normally distributed, which means it fits in a bell curve.
So this one is normal.
Yeah, bell curve equals normally distributed. They're the same thing. They're just different words. Like answer and solution. Answer, solution, x-intercept, they're all the same thing. In algebra. If the data is not normally distributed, if it's not normally distributed, then we can't use the 68, 95, 97, 9.7 rule. It's not empirical. We use the Chebyshev rule or Chebyshev method. The Chebyshev theorem states this. The proportion of any set of data lying within K standard deviation of the mean is always at least 1 minus 1 over K squared value. Okay, why is it 1? It's 1 minus 1 over K squared. K is the standard deviations. The reason it's 1 minus this ratio is because 100% is equal to the number 1 in decimal. So what this says is 100% of your data minus this many percent of your standard deviations will give us the approximate percent value of your solution set. Where K is any positive number greater than 1. Where K is any positive number greater. Why does it have to be greater than 1? Because first off, it's a counting number. Standard, how many standard deviations do you have? 1, 2, or 3? So that's why it has to be a positive number. It can't be 0 because you can't divide by 0. So that's why it's any number greater than 1. And typically we use only integers too. So we're looking at whole numbers really. No, in counting numbers, natural numbers.
Professor, what's that word right there after is?
Is any
Oh, okay.
positive number greater than 1?
Thank you.
I'm sorry, thank you. At least 3/4, which is 75% of all data values lie within two standard deviations of the mean. How is that different than our empirical bell curve? What is the bell curve at two standard deviations? 95. So this is only 75%. Again, this is not normally distributed. This is any other weird shaped data. And then we have another property. The next one is at least 8/9 or 89% of the data of all data values lie within 3 standard deviations of the mean. Example. Example 7. IQ scores have a mean of 100 and a standard deviation of 15. What can we conclude from Chebyshev's theorem? So what can we conclude from Chebyshev's theorem? Remember, Chebyshev's theorem says the proportion of any set of data lying within k standard deviations of the mean is always at least 1 minus k over 1 over k squared. We're looking at a standard. What can we conclude about theorem? So when k equals 1, K equals 2, and K equals 3. One minus 1 over K, we're using 1 over K squared, so it's 1 squared. Remember, can we use 1? No, because it says use, it has to be greater than 1. That's the reason why. Because if it's 1, there's nothing really there. 2 standard deviations, which is 1 minus 1 over 4, which is 4 over 4 minus 1 over 4 makes it 3 over 4. So within 2 standard deviations, we have 75% of our data. One minus 1 over 3 squared, 1 over 9. 9 over 9 minus 1 over 9 is 8 over 9. Approximately 89% of our data fall within 3 standard deviations. And then approximately 11% is outside the 3 deviations. So far, so good. How do we know in example 7, we got to use Chebyshev's besides that? Besides giving us, how do we know that we're gonna have to use that? From with what the statement said. Because the statement never told us that the data was normally distributed. It simply said the mean is 100, deviation is 15, which means nothing to us. We can take it for, we can assume that it's standard deviation, normally distributed, or we can be safe and use Chebyshev's, which is not normally distributed. You're going to see examples where it's not normally. For example, what does skewed, positive skewed look like? Or skewed right? What does skewed right look like? Like that. Remember the skewed right, look at your right foot, your big toes here. Can you use the bell curve idea on here? Because here we have the mean is right there. So we can't use that 68, 95, 99.7. You can't use that. So we'll have to use Chebyshev's theorem here. And chances are your data will usually be skewed when you collect it.
Which states this is Cheby's theorem or bell curve.
Yeah, the question is when do you use which? You only use the bell curve if it's normally distributed. In other words, if the mean is actually in the middle, where 50% of the data is both sides. If it's not, then the only thing we can use is Chebyshev's.
Like this Swiss of told us 100 mean of 100 and a standard deviation of 15.
Well, yeah, because it never tells us that it's normally distributed. Okay, what about when we compare 2 different samples? Comparing variations of different data sets. It could be a sample, it could be population. So our example here is we have our ride. We're gonna do the rock and roller coaster. And then we use the Tower of Terror. The mean is the same. That doesn't help us any. The median is the same. That doesn't help us any. So what do these first three columns tell us? What does this first column tell us? The mean. The average wait time is 57.3 minutes, almost an hour. The median, the middle wait time is 55 minutes. It's pretty close to the mean. The mode is 45. That means most people only wait 45 minutes. The mid-range is 62.5. What is the mid-range? Right, take the two extremes and divide by 2. So what does that tell us? Which ride would you do better on to get a ride faster? Which one? Tower of Terror? Why? Yeah, the deviation is only 12.1, which means that your data, if it's around the mean, it's much closer. So it means all the times are about the same. So you can budget your time. The rock and roller coaster, it's a flip of a coin. Whether you when you get in line, whether you'll be 15 minutes or 120 minutes. And all of these lines in Disney World, doesn't matter if it's sunny or raining, people won't move. They won't get out of line. The first time I ever went there, it was pouring down rain. Nobody moved. They said it always happens this way. Middle of the day in Florida, it always rains. So if you get out of line when it rains, you never get to a ride. So you just wait it out. Now, in order to compare these, we have to do something called the coefficient of variation. To determine which is better, we use the coefficient of variation. or the CV. What this thing does, it describes your standard deviation relative to the mean and sees which one's averaging out better. Because whenever you divide anything, you're looking at an average. So we also have between samples and populations. For sample, remember we use standard deviation, which is S divided by the mean times 100. The reason we multiply by 100 is anytime you take a fraction divided by 100, divide by the mean times 100, you get a percent. This will give us some percent value. The population, the standard deviation of the population is the rho. The mean is the mu times 100. Let's look at an example here. Yes.
Symbol of population.
This one?
That was the-
This is a row, that is 0 with a little squiggly on top. That's the population. Anytime you have Greek letters, you're dealing with a population. So the row, the circle with a little swoopy at the top, is the population standard deviation. The mu looks like a cursive U, is the population mean. So let's look at the last example of this section. Example 9. Heights of adult males and weights of adult males. Using the data set of body weights, which if you want to, I'll send it to y'all. But for the heights, the mean of the sample was 174.12 centimeters. And the standard deviation was 7.10 centimeters. That's the heights of the adults. The weights, the mean of the adult males, the weights was 85.54 kilograms. And the deviation was 17.65 kilograms. What are we looking for? Compare the variations among the heights and the weights. So to compare the two, we have to look at the coefficient of variation. And the smaller the number, the better it is. The more accurate it is. So the CV of the heights versus the CV of the weights. The formula says the standard deviation divided by the mean. So it's 7.10 divided by 174.12 times 100. .1 divided by 174.12 times 100. 4.1%. And the other one, the standard deviation is 17.65 divided by 85.54 times 100. Is 20.6%. So the coefficient of variation of the height is 4.1%. And the coefficient of variation of the weight is 20.6. So what does that tell you? That the heights are more proportional than the weights. Well, think about it. Can you control your height? Can you control your weight? So yeah, so that's why if you leave it to us to take care of ourselves, it's not going to happen. That's what this is telling us. Nature's off by 4.1%. We're off by 20.6%. All right, that's it for that section. So we have like 10 minutes left or 15 minutes left.